All right, let's continue. So with radial kernel, which is just a different function. So the formula is in your textbook, but with that function, some function k, the feature expansion that we're going to have with the kernel, which is automated, so it takes care of it for us, is actually equivalent to expanding the features to some infinite dimensional space, finding the hyperplane that separates them, and then projecting everything back to the feature space. So then with radial kernel, there is some hyperparameter gamma that that controls the roughness of boundary, and also it does some regularization for us. So then for the nonlinear example we had, where is it? Here, something similar to this. We had x1 and x2. We had some circles here, some circles here, and some x's in between. Then with a radial kernel, essentially it expands the feature space to some infinite dimensional space. So P is infinity in that new space. And that's as good as it gets for finding the hyperplane, because we saw that with this example, which was nonlinear, when we moved from 1D to 2D, everything changed. We changed the problem from a nonlinearly separable problem in 1D to a linearly separable problem in 2D. So now you can imagine what happens if we go to infinitely dimensional space. The problem becomes very easy for the computer. So then it finds the hyperplane in that infinite dimensional space and then project everything back to the feature space. Then the boundary we're going to have will be something like, let's say something like this. The boundary would be something like this, with a margin for x's in here, and I guess some margins for o's in here. So this is still, supervised learning, but now it's becoming more and more similar to clustering. So it kind of founds this cluster of x's and separates them, rather, accurately. So yeah, so this is radial kernel. It has this hyperparameter that should be tuned by cross-validation. So then when we look at the performance, yeah, so that's the next topic. So when we look at the performance of our classifier using ROC, so here we have fallout or false positive rate, and on the y-axis we have recall. So there are a couple of examples in your textbook, but let's say on the test data, for some binary classification task about heart disease, predicting heart disease from, I guess, 14 features, then performance of LDA is something like this, and then performance of SVC, the test performance of SVC is something like this. So this is SVC, or support vector classifier. And then the performance of SVM with radial kernel depends on the value of lambda. So in that example, I think there are some cases where lambda is tuned properly, and we get some SVM, let's say with lambda equal to 10 to the minus 2. So this is like, let's say, the tuned value for the suitable for complexity of the heart disease dataset. When it is tuned properly, we get some additional performance, some performance better than SVC. But if we don't tune it properly, we may also maybe overfit to the data and get some SVM, maybe with a small, roughness parameter that would, even underperform LDA. So what we covered so far was support vector machine, from the very basic idea of separating hyperplanes to then using a maximal margin classifier, then a soft margin, then feature expansion, and then automating that feature expansion. So support vector machines would be an algorithm in which that feature expansion is automated using some kernels typically. But all of these were just about binary classification, because when we have a hyperplane, we have just two regions. So what can we do for multi-class classification? So here, the classification gets a bit ad hoc. We need to make some changes. So for multi-class classification, using SVC or SVM, we need to either compare one class to all other classes, or compare one class to another class, but do all the pairwise comparisons. So for multi-class classification with SVM or SVC, one method is one versus all. Another method is one versus one. Yeah. So with one versus all, what we need to do is we need to fit, let's say for multi-class classification with k classes, we need to fit k binary classifiers. Each of these binary classifiers would be one versus all. So for each of them, we need to define some kind of, mega class, including everything but one class, and then make a comparison between that one class and all the other classes. And then we see what is the class that just has a higher likelihood compared to all the other classes combined. So let me give you an example with the Iris dataset. So you may remember that with the Iris dataset, we had 3 classes. We had Setosa, Versicolor, and Virginica, right? So as with the Iris dataset, k is equal to 3, so we need to fit 3 binary classifiers. So binary classifier 1 is going to distinguish between Setosa versus rest. So Setosa versus Virginica and Versicolor combined. Binary classifier 2 compares Versicolor versus rest, and binary classifier 3 compares Virginica versus some mega class of Versicolor and Setosa together. Then if we have some test observation X star, we're going to look at p hat of X star from the first binary classifier. So let's say from the first binary classifier, p hat is 0.01 because it just didn't have the features matching with Setosa. So this one was much more likely. It was 99%. This one was 1%. Then based on the second binary classifier, we see that p hat, so this is, let's say, p hat 1, this is p hat 2 of X star is now 0.6. So relatively, so far we can see that it's much more likely for the sample to be Versicolor compared to Setosa. But we still need to continue. And then based on binary classifier 3, we see that this one is 0.7. Therefore, based on these, we classify X star to Virginica. So all of this is OVA. Then we have OVO, which fits k choose 2 binary classifiers for pairwise comparisons between classes. So let's say there is some binary classifier 1 that classifies kind of distinguishes Setosa from Versicolor. There's a second binary classifier that distinguishes Setosa from Virginica. Binary classifier 3 has Versicolor versus Virginica. So we have these 3 binary classifiers. We were a bit lucky because 3 choose 2 is still 3. But when k is large, the number of binary classifiers we have in OVO is much larger than k. So then let's say for some test observation, here we classify based on the class that wins the most comparisons. So this is sort of a competition between Setosa and Versicolor. Let's say the estimated class is Versicolor. For this one, the estimated class is Virginica. This is just because the sample didn't have those specific features of Setosa, because Setosa was totally different. And based on this last one, we see Virginica. So you can see that Setosa won none of these competitions. Versicolor won one of them, and Virginica won 2 of these competitions. So we classify X star to Virginica. Any questions? Yeah.
class is ordinal.
So odd?
The class is ordinal. So when the class is ordinal.
Ordered.
Ordinal.
Sorry. Ordinal.
Yeah, ordinal.
I cannot think of like any specific consideration. So if it is ordinal, maybe we can just define the problem as a regression problem. I mean, just in general, like not about support vector machines. I'm not sure if we need to do something special here. Yeah, perhaps there is some specific methodology for ordinal data, but at least I don't know any. So in this case, I mean, if the task is classification, this is how to deal with it. And usually we use support vector machine for classification. For regression task, I guess we use regression. All right, so this OVA I think OVA is the preferred choice where K is large. Otherwise, if K is small or moderate, the preferred choice is using OVO. This is because, I mean, these comparisons, I think here was sort of unfair, you know, because this is like a mega class. But here, I think it's just more intuitive because here we were doing the easy parts of the classification. This is also easy because versicolor and virginica are both different from setosa. So this separation is easy. And then between these two classes that are somewhat, you know, kind of intertwined, a support vector machine can separate these with, you know, feature expansion. And then if this last one says virginica, then we would just classify to virginica. So that's why the preferred choice is always OVO, but the main issue is the computation because we need K-choose-2 binary classifiers. So if it is 10-digit handwritten classifier, sorry, if it is handwritten digit classification, which has 10 classes, then it would be 10-choose-2, which is 55 or something, right? So we need 55 binary classifiers. And then for every single test, we also need to check 55, you know, estimates. So that's why maybe this would be the suitable choice. We just need 10 binary classifiers. All right, so any questions about multi-class? All right, so we saw that support vector machine you know, does a lot of exciting stuff, especially if our focus is on predictive performance for high dimensional data. It is definitely, you know, adding some new functionalities to our toolbox. So for predictive performance, especially with high dimensional data, SVM definitely has some advantages. Then I guess also for yeah. Working with separable data, of course, SVM has no issues with that compared to logistic regression that has unstable parameters if the data is separable. So if the task of classification is easy, actually logistic regression is not a suitable choice. SVM, on the other hand, has the flexibility to handle an easy classification task or a complicated, you know, non-linearly separable task. When we have high dimensional data, of course, for logistic regression, we need some regularized version. So normally, just the simple version of logistic regression also fails for high dimensional data. So these are pretty much, you know, I guess what we would care about from a computer science perspective. And SVM is also like developed by some, you know, applied mathematician from Soviet Union. So SVM is maybe from 30 years ago. But it's, you know, kind of magical that 30 years ago we had these really, I think, fancy ideas of going to infinite dimensional space and finding a hyperplane and coming back. So definitely, you know, some features of SVM are exciting for the right reasons. But then from a statistical perspective, there are reasons that we need other methods. For example, for estimating probabilities of classes, actually logistic regression does a much better job than SVM. So SVM is not based on a probability model. There are ways to kind of extract something similar to probability from SVM, but that's sort of a post hoc analysis on the result of SVM. While logistic regression is based on odds ratios and probability. So that's why, you know, from a statistics perspective, there is still, you know, reasons to consider logistic regression. And then another sort of comparison is between SVM and models that are explainable. For example, in, let's say, explainability and feature selection. So for explainability and feature selection, we had like regularized fitting, we had like ridge and lasso regression. So again, from a statistical perspective, there's still some advantages that ridge and lasso provide and SVM does not provide. So if we care about explaining, where a prediction comes from, ridge and lasso still, offer some benefits that are not offered by SVM, which is kind of expected. Also here, if it is classification, we can have linear regression with regularization. So, so this is meant to kind of tell us that all these like magical things about SVM is not everything that we care about, especially in statistical learning. There are also these considerations that are relevant, and yeah, that's why there is still some room for all these other models that may suffer from some other issues or may not have necessarily the same level of predictive performance as SVM. So yeah, I think I covered everything. Any questions? Yeah. So if the data is separable, this means that the classification is easy. So one example is classifying setosa versus versicolor, for example. When you look at the feature space, they are linearly separable. So it looks like this. This is sepal and length and petal length, something like this. Actually, for a case like this, as the probability of a class for logistic regression would be so close to 0, and probability of the other class would be so close to 1, then the odds ratio would be something like 1 divided by 0. That's why this is a bit counterintuitive that logistic regression is not suitable for easy classification tasks. This is partly because logistic regression comes from context of medical sciences where nothing is linearly separable. So it's about measuring the probability that the patient has a positive reaction to some treatment, for example. As human body is so complex, the task is not as simple and trivial as this. So then if we use logistic regression, which is suitable for more non-trivial tasks, if we use it on a trivial task, it's going to disappoint us. Yeah. Any other questions? Yeah.
What's the point you're trying to make there in the roughness and performance? That the smaller roughness always perform better, or you mean only a suitable roughness?
Yeah, roughness is this. Smoothness and roughness of this this boundary. So I would say this is a very rough boundary, and we would get this if lambda is large. And a smooth boundary would be something like this, and we get this when lambda is small.
Okay, so what's the point you're trying to make in the performance graph?
Yeah, in the performance, so eventually we're going to use SVM for certain tasks, and there is no one value for lambda that is always suitable. It depends on the complexity of the task. So the example in your textbook is based on some data set on heart disease. So it's a binary classification of whether someone has heart disease or doesn't have heart disease. And there are also, ground truth on that. So if someone actually does some angiographic test, that would be the result of that test, which is more expensive and takes time, is the ground truth for heart disease. But the idea in that predictive analysis is predicting whether someone has heart disease or not based on 14 easy to measure features. For example, I guess cholesterol, age, different sort of measurements from blood tests and so on. Considering that blood test is much easier than angiographic test, right? And then for that classification, we can see that SVM has a performance which is quite close to the ground truth, meaning that with those, inexpensive medical tests like blood tests and so on, and a support vector machine, we can predict whether someone has heart disease or not pretty much with the same level of accuracy as an angiographic test. And then here, when we do the parameter tuning properly and lambda is tuned properly on the test data set, we see that SVM is outperforming SVC. But if we don't do the hyperparameter tuning for lambda used in RBF kernel, used in SVM, we may end up with an SVM that has even a lower performance than LDA. Yeah, so LDA in here is meant to be some baseline of a very simple classifier. So if we do all this complicated stuff and eventually get a performance less than LDA, that's not good, right? Other questions? So sorry that the topic was a bit abstract. I tried to motivate it, but also make sure to check your textbook to complement your learning on this topic. Thank you very much, and see you next week.